Every method in this series finds the same root, but not at the same speed. Here is the error on a log scale as the iterations go on. Bisection halves the bracket every step. It is steady but slow, so a straight line down. Newton plunges, same problem, a completely different shape. So what exactly makes one method faster than another? Let's see it precisely. Welcome back to Numerical Methods episode 7. Order of convergence, the one idea that ranks every root finder we have built. First, the definition. Let En be the error at step n. How far xn is from the true root p. A method converges with order alpha if the errors settle into this relationship. Alpha is the order. Lambda, a positive constant, is the asymptotic error constant. We don't assume alpha, we find it later by watching the real errors settle. So let's place every method on one scale. Order 1 is linear. Between 1 and 2, superlinear. Order 2 is quadratic. The bigger alpha, the faster the error dies. This is the definition from Burden and Fairs from their error analysis section. Two anchors are worth feeling in your bones, linear and quadratic. One fact first, the number of correct digits is about minus log 10 of the error. Linear convergence multiplies the error by a constant each step. So it adds a fixed number of correct digits every step, a steady climb. Quadratic convergence multiplies by the error itself. The error gets squared. That roughly doubles the correct digits every step. 1, 2, 3, 4 versus 1, 2, 4, 8. That gap is the whole story. Where does the order actually come from? One Taylor expansion answers it. Write any method as xn plus 1 equals g of xn with the root a fixed point. Subtract the root. The new error is g of xn minus g of p. Taylor expand g around the root at p plus en. The g of p terms cancel, leaving the error recurrent. If g prime at p is not 0, the first term wins, linear, order 1, constant the size of g prime. Take this series fixed point map, g is x plus 2 to the 1/3. Its derivative is 1/3 times x plus 2 to the minus 2/3. At the root, p cubed equals p plus 2, so that factor becomes p to the minus 2. So lambda is 1 over 3 p squared, about 0.144. Now Newton. Its map subtracts f over f prime. Differentiate it with the quotient rule. The ones cancel, it collapses to f primes f double prime over f prime squared. At a simple root, f of p is 0, so g prime at p is 0. The linear term dies. What's left is the squared term, with g double prime equal to f double prime over f prime. So Newton's constant is f double prime over 2f prime. Put in our function x cubed minus x minus 2. Its first derivative is 3x squared minus 1. Its second is 6x. So lambda is 6p over 2 times 3p squared minus 1. Cancel the 2. 3p over 3p squared minus 1. That's the constant from the table, quadratic. Newton is fixed point iteration, tuned to kill the linear term. Put every method we have built on the same problem and rank them. Method, order and the asymptotic constant on x cubed minus x minus 2. Bisection, order 1 and that 1/2 is the bracket, not a true error constant. We'll come back to that star. Fixed point iteration, order 1, constant about 0.144. Newton, order 2, quadratic, constant about 0.77. Secant, order 5, the golden ratio, 1.618, superlinear, no derivative needed. And Müller from the last episode, order about 1.84. We derived fixed point and Newton in full. Secant's phi and Müller's number come from a similar but longer argument. We'll take them as given. And notice, Newton and secant share the very same constant. They spend it differently, but it's the same number. We won't prove these orders. We will watch them happen from the real errors. The error is the distance from xn to the true root p, and lambda is whatever the error ratio settles to. Let's do Newton's first step by hand. Start at x naught equals 1. F of 1 is minus 2, f prime is 2, so x1 is 2. The error is the distance to p, about 0.48. Step again to x2, 1.64, with error about 0.11. So lambda at step 1 is e2 over e1 squared, 0.502. One more step gives x3, error about 9 thousandths. And lambda at step 2 is e3 over e2 squared, 0.68. Keep going, step after step, Newton's rule, order 2. The error falls off a cliff. At that ratio, our measured lambda parks on 0.768. Secant needs two seeds, x0 is 1, x1 is 2. Its update gives x2, 2 minus 4 sixths, which is 1.33. Now the three errors, about a half, and 1/8. Its two-step lambda is e2 over e1, e0 about 0.75. Keep stepping. The ratio wanders up to 0.887, then settles. Its error crashes to just a little slower. The ratio wanders, then settles on the very same number. Side by side, same problem, two speeds, one constant. Both errors reach about 9 digits, but Newton by step 5, secant only by step 7. But both measured ratios land on the same lambda, and it's exactly the value we derived, f double prime over f2 prime, measured, not asserted. We have ranked them by order. Now watch all 5 rays on our running example. Error on a log scale against the number of steps. Lower is better. Bisection order 1, the slow lane, a shallow straight line, fixed point. Also order 1 but a steeper line, a smaller constant. The secant order 5, about 1.62, it curves and pulls away. Müller order 1.84, a genuine cliff. And Newton order 2, almost the same cliff. That's how close 1.84 and 2 are. The same story in numbers, step to 9 digits, ranked by order. Notice Müller ties Newton here. Even at lower order, its 3 seeds are a head start. Order sets the asymptotic speed, the starting guess does the rest. Two honest footnotes, because the clean table hides two subtleties. First, bisection, its one half is a bound, not a limit. Measure the error from the true root. The midpoint lands close by luck, then jumps away. So the error even grows. The ratio hits 10.7. Across all steps it bounces 10.7, then 0.45, 0.40, never settling. What's guaranteed is the bound. The bracket halves cleanly every step. Second, Newton's quadratic speed assumes a simple root. At a root of multiplicity m, write f as x minus p to the m times q. Differentiate with the product rule and factor out x minus p to the m minus 1. In f over f prime, that shared factor cancels, leaving this. Let me clear the earlier lines and take the limit. As x approaches p, the x minus p q prime term dies and q cancels, leaving x minus p over m. So each Newton step removes only a fraction of the error, 1 minus 1 over m. That's linear, constant m minus 1 over m. Take a clean double root, f equals x minus 1 squared. Newton collapses to xn plus 1 equals xn plus 1 over 2. The error just halves, 1, a half, a quarter, an eighth. That's lambda 1 half, no faster than bisection's bound. That's order of convergence, the ruler we'll use for every method from here on. To recap, alpha is the order, lambda the constant. Bigger alpha means the error dies faster, and Newton and secant secretly share the same constant. So far we have been finding roots. Next time we flip the question. Given a handful of points, what curve passes through them? That's interpolation.